So we're just gonna wait a couple minutes for some of the other people to show up. Hello. Now I can see people. I think we'll get started then, and whoever's gonna show up later will just show up later. Oh, somebody else is coming in. So I shall save my, well, might as well do it right now. So yesterday we went over as much of chapter 1 as I could. And so today we're gonna go through all the different rules of differentiation and derivatives. We're gonna talk about average rate of change, instantaneous rate of change, and then we're gonna do all these crazy different differential rules. Hopefully you have most of these memorized because I'm gonna ask y'all to participate by typing in the chat box. So first things first is I set up a quiz. How do I get this quiz to go? Here you go. Quiz number 1. We have these 3 questions that I want you to answer. So first one, we get that the limit of f as x approaches 0 is 5. Which of the following is true? You can choose which one you think is true there. And then we also have question number 4. It says if a function of f is differentiable when x is equal to x, which of the following must be true? And then there's a third question. So I listed a bunch of possible conditions for intermediate value theorem to apply. There are multiple that are correct there. So for question number 3, you can select multiple. So take a second, look through those, see what you think. We are doing a pop quiz really quickly over stuff we did yesterday. I'll give about 10 more seconds. We'll see if anybody actually answers. Nobody's answering. Okay. So number 1, if the limit does indeed exist, then that means the limit from the left-hand side is equal to the limit from the right-hand side, right? So the limit of this is equal to this limit as x approaches 0 plus of f of x, right? But we do not know if the point exists, right? So a perfect example would be a removable discontinuity. So for number 7, the answer is D, only 1 and 2 are true. Okay, for number 4, if a function is differentiable, remember we talked about last time that if something is differentiable, then it is implied that it is continuous as well. So if something is continuous, then 1, the limit does exist. 2, if something is continuous, then the point also exists at that value. And then 3 is obviously true, I just showed you because we said differentiable implies continuity. So then we have D. And then finally, we have what conditions must be met for intermediate value theorem to apply. Remember that number 1, the function must be continuous along some interval. So we'll just say A to B. Okay. And then the other thing is that the y value, so it's the y value, let's say some L is between the two y values that they give you. And remember that this interval must be a closed interval. These are the 2 conditions that must be met for intermediate value theorem.
Y for continuous, is it open, and differentiable, it's closed?
I mean, that's just the definition of the intermediate value theorem. Honestly, you really don't need to know this part because usually if it shows up on a free response question, it's just gonna be a polynomial, or it's just gonna say the entire function is continuous. So this part I just wrote as extra stuff. You just need to know this part. Alrighty, so then let's move on to the stuff of today. So, oh, before that, I don't know if anybody had a chance to go over the homework. I'll get, feel free to ask a question if you want to. You can unmute yourself. If not, I'm gonna move on to the derivatives. And then if we have time at the end of this, we'll come back to this. Okay. We shall do derivatives today. So I'm gonna need all your help here. So if you wanna speak, you can speak. If you wanna type, you can type. But does anybody remember the limit definition of the derivative? So remember that derivative is the form of the slope. So I'll do the alternate form first. We can do this, f of b minus f of a over b minus a. Right? Except instead of this being a constant value b, we can replace this with f of x. So this is your average rate of change. And remember, if we're doing derivatives, it'd be the limit as x approaches a. So this is one of the forms. We also have the other form. This is the one that's more common. Right, f of x plus h minus f of x. Right, this is just saying we have this y point here, and then this one's moved over just a hair over h. And then this one is limit as h approaches 0. What about the different ways of notating derivatives? We have f prime of x. We can do d dx of the function. We can say y prime. We can do
with
d.
a number.
Which one?
Like past second derivative, you don't use a prime, you just put like f of 3, f of 4.
Yeah, so when we're doing higher order derivatives, so we can do f double prime, right, like this. And then when you get beyond that, you can do f of some sort of number here. So this may or may not be familiar to some of you, right? So in case you see this notation, this is, you're saying you're finding the nth derivative of some function. So that is true for higher order derivatives. Okay, we also have, what does the derivative tell us when x is equal to a? So you all need to be able to either go backwards or forward with this. So I use IROC, right? Instantaneous rate of change.
Like the slope of that x value?
Yes, exactly. So we have the slope of the tangent line at that x value. Perfect. So these are the two most common ways they're going to say derivative without actually saying derivative. So make sure you keep that in mind. And then now we need to figure out the difference between differentiability and continuity. Can somebody use their own words to help me figure out the difference between these two?
Isn't differentiability when the slope of the tangent line is the same going from the left and going from the right?
Yeah, perfect. The limit of the two derivatives is equal from left and right. Yes. Slope of tangent line is the same. Tang lin is same from both directions. Good. Or another way we can say differentiable is we can say you can take the derivative, right? You can take derivative. Right? Versus continuity. Continuity, last time, what did we say? Continuity is just you don't have to lift up your pen, right? You have no holes, no cusps. Oh no, we can have cusps. You have no holes, no asymptotes, right, etc. No jumps. Cool. And then we're going to review all the different types of derivatives. Power rule. So assuming that a and n are constants, what's the derivative of this one?
A n to the x to the n minus 1.
A times n x to the n minus 1. Perfect. And then we have, let's go to derivative of sine. Everybody should know that one, right? So I'm just going to write cosine of x. Ta-da. And then cosine, right? So all the ones that start with a c, cosine, cosecant, cotangent, they always end up with a negative derivative. That's how I remember it. Product rule. Does anybody have a good song for product rule? No songs. I have a song for the quotient rule. I just don't have one for product rule. I was hoping somebody had one. I do f g prime plus f prime g. That's my way of doing it. I'm sure other people have other ways. I guess I can share my song. My song for quotient rule is low d high minus high d low over the square of what's below. There's no notes to the song. I guess it's more of a rap. Who remembers the derivative of ln x? You can just unmute yourself if you want.
1 over x.
1 over x, perfect. And then e, there's this really cool meme of this knight with a sword trying to like take the derivative of e to the x, and every time he takes it, it's still the same like dragon that he's trying to slay. So e to the x is e to the x. 1 over x, remember that can be written as x to the negative 1, so the derivative of x to the negative 1 is equal to negative x to the negative 2, aka 1 over x squared negative. Rad x, don't forget that radicals can be written in exponent form like this. So then we get 1/2 with the rad x in the denominator. Cool. Chain rule, who can tell me what chain rule is? when you have a composite function, a nested function, some people call it, remember that you take the derivative of the outer function first, do not touch the inner function, and then you multiply that by the derivative of the inner function. So for a lot of these, this is slightly different, right? Now we have a derivative with respect to x, but then our function is in terms of u. So when you have power rule, this one would be an times u to the n minus 1 du, or u prime, depending on which one you use. So this would be another version of chain rule, right? So eu would be e to the u du. Sine of u would be cosine of u du. Cosine would be negative sine of u du. Does anybody remember how to take the derivative of an exponent?
So like AU, DU, ln A.
Yeah, so I put the ln a in front. Ln a, au, du, like that. Okay. Tans. So remember, my student told me this once. She said tans are sexy. So that's how she remembered that the derivative of tangent u is secant squared u. Secant is secant u tangent u du. Cosecant. Cosecant is the same as secant, right? So except everything has the cofunction instead. So it's negative cosecant u, cotangent u, du. And then we have cotangent, which would be the same as tangent. It's negative cosecant squared u du. Give me a second. I just have to resend an invite to somebody who is stuck outside of the room. And while I'm sending that email, look at this question number 1 and see if y'all can start working on that one to see what you get for dy dx. So we're going to take the derivative of this with respect to x, right? So we take the derivative of x squared, that's just 2x. And then if we take the derivative of this one's pretty easy too. This one is 4 times 5y to the 4th y prime, or dy dx. I'll just write y prime. And then the derivative of this one, right? This is just 100, or 0. Excuse me, I keep forgetting. When you take the derivative of a constant, it's 0. This one in the middle, though, this one's problematic because we have our product rule here. So it's minus 3 parentheses. I'm just going to put this whole product in there. All right, so it'll be first times the derivative of second plus second times the derivative of the first. Derivative of x is just 1. So then what do we get? We get 2 minus 3x y prime plus y plus 20 y to the 4th y prime equals 0. We isolate all the y prime terms on the same side. So these two have the y prime terms, so we get negative 3x y prime plus 20 y to the 4th y prime minus the other 2 over. So you get negative 2x minus y. Factor out that y prime. Right, and now we can just divide by that whole thing. So y prime is equal to negative 2x minus 4 over the thing that we just factored. Hope you can understand my chicken scratch. Any questions? Alrighty, switch to another color. Let's do blue. Close this out. What do y'all think of the next side? Find the derivative of b with respect to t. Oh, given that, sorry, that is the derivative, excuse me. So find the second derivative. Well, what are we gonna do? Let's attack the both sides by taking the derivative with respect to t, right? And if we take the derivative of the left-hand side with respect to t, we get this notation, right? D squared b over dt squared. Right, this 6 is a constant, stays out in front. This radical, so the 1/2 power. This is 10 minus b, negative 1/2 power, power rule, right? Times by the derivative of what's inside. The derivative of what's inside, this is a b. So it's gonna be negative 1, right? The derivative of a variable is just 1 db dt, because we're taking with respect to the variable t. Let's do some simplifying. 6 times 1/2 is 3. If I want to rewrite the square root to the negative 1/2 power, I can rewrite it like this, right? You don't have to for the AP exam. I'm just doing it. And then this negative 1 dB dt. What the heck was dB dt? dB dt was this thing. So I can just take that thing and plug it in. So times negative 6 rad 10 minus b. It looks like the 10 minus b's cancel out. Badoop, badoop, negative 18. Questions? Okay. And so this one's a fun one for people. Let's use the chain rule to figure out how to find the derivative of an inverse function. So y'all should know that if they ever give you this notation, this is implying that h of x and g of x are inverses. I don't know what I'm writing about, it's already there. So this is true, right? So let's take the derivative of both sides with respect to x. When we take the derivative of both sides with respect to x, we get h prime of g of x times g prime of x. Right, on the right side, when we take the derivative, we just get 1. And so we have this expression is true. And sometimes in textbooks, you might see it rewritten as the derivative of g can be rewritten as 1 over h prime of g of x. Right, that might be in a textbook. Or they might have it written this way in textbooks. They'll say the derivative of an inverse function, so that's f of minus 1. And then the way they say is derivatives by writing it like that. The derivative of an inverse function is equal to 1 over, instead of h, they write regular f, of the inverse function of x. Pretty gnarly, right? But they're not going to have you do it this way. So I'll show you a quick way of doing it for with example number 2. So they give us this point, right? So this is saying that x point is 2 and the y point is 7. That's how you get f of 2 is equal to 7. So whenever you see that and you know you're dealing with an inverse function question, you can say f of 2 is equal to 7, and then you can say f inverse of 7 is equal to 2, right? These two statements are true because when you have an inverse function, by definition, you switch the x's and y's with each other. We can even make a pretty picture here. right? So if I have the point 2 comma 7, imagine that there's 7 dashes there. Then I can go ahead and plot another point that has 7 comma 2. Let me use a different color. 3, 4, 5, 6, 7, 1, 2, right? So these are the 2 points, right? So this would be this one. This one would be this one. And then what? They tell us that the derivative of 2 is equal to 5. Well, if we know the derivative at 2 is 5, then we know the slope of the tangent line is 5. So the slope of the tangent line is 5, which is something like that. Remember that slope is something also like dy dx, right? Well, what is an inverse function? Inverse function is when you switch the x's and the y's. So then the slope of this thing will equal 1 over 5, right? The slope, you can think about the slope of this line over here as just the reciprocal, which is kind of like saying dx dy, even though it isn't necessarily. Questions on that one? Okay. So then you can do something similar over here with this, this one too, right? If we work backwards, right? So if we work backwards, we're given, let me zoom in so I can write a little bit more here. We're given that the slope of the inverse function is 5, or we don't know what it is. We're trying to find it, right? And that means we need to find the value of the inverse function at 5 equals something, right? So then if we go backwards, we need to find what value of this function is going to give us 5. So we need to find this number here, which is the same as that number there. So what do? We set this equation equal to 5. So we plug in 5 is equal to the cube root of 2x minus 1. We cube both sides, so you get 125 is equal to 2x minus 1. 126 equals 2x. X is equal to 63. So we know that P of 63 is going to give us 5. So then we need to find the derivative when we plug in 63. So when we take the derivative of that, what do we get? We get 1/3 2x minus 1 to the negative 2/3 power. Don't forget the chain rule, times 2. This is equal to P prime of x. I need to make this pen a little bit less wide. It's taking up too much space. And now we can go ahead and plug in the number 63 that we got earlier. 1/3, 2 times 63 minus 1 to the negative 2/3 power is equal to times 2. The 2 and the 1/2, oh, that's a, whoops, they don't cancel because that's a 1/3, not a 1/2. So we get 2/3 here. And then I'm sure that everybody knows that when you take 125 and raise to the negative 2/3 power, you get 1 over 25. JK. So this is 2 over 75. We found the slope of our tangent line is 2 over 75. So then the slope of our inverse function tangent line is going to be 75 over 2. That was a lot. Any thoughts or questions from anybody on this one? Okay. So we've done the first 3, right? I think for the last 3, I don't really think they're going to show up on the test, but you should have them anyways, right? So anybody remember the arc sine of u, the derivative of that? 1 over rad of 1 minus u squared du. I'm not going to go ahead and show the proof because that'd take forever. Just have these. And then note that arc cosine, right? Arc cosine and arc sine can be written either using the letters ARC or using this -1 exponent. Right, so this is going to be negative 1 over rad 1 minus u squared du. And then arctan. So arctan is going to be 1 over 1 plus u squared du. Questions on those? So just make sure you have those easily accessible in case you need them. I don't think you're going to need them. Okay. So part of knowing how to do derivatives is if you're comfortable with the derivative rules, you still need to know how to approach a derivative because there are a bunch of ways of doing a derivative, but you want to find the simplest way. So for example, number 2, the first one's really easy. The derivative of 1 over x, we can do negative 1 over x squared. The derivative of sine of x is pretty easy. It's just -3 cosine of x. But what would be the simplest way of taking the derivative of this crazy looking thing? Don't do quotient rule, please don't. Anybody? So whenever you have a binomial on top and a monomial on bottom, you can actually split it up into 2 separate fractions. So before I do this derivative, forget I took the derivative, right? So we can rewrite this thing as 4x over 3, and I'm going to convert this to exponential form, 3x to the 1/3 power plus 2x to the 1/2 power over 3x to the 1/3 power. And don't forget the rule that when you're dividing exponents, you subtract the exponents from each other, right? So this simplifies to 4/3 x to the positive 2/3. 1 minus 1/3 is 2/3. And then this one is 2/3 x to the 1/6 power, right? And then from there, then you can take the derivative. What about number 3? We can do the product rule if you really want. Any other ways of taking the derivative without having to use the product rule?
Multiply it out.
Yeah, multiply it out, right? Multiplying something out will make it easiest to do it that way. Cool, so FOIL out. I don't know why I highlighted number 4. Number 4 is the same thing, right? When you get radicals, just make sure to convert them into exponents. Number 5, just to remember that when you have something to the -1 power, -1 power is just saying take the reciprocal of it, right? So this one just x squared over x to the 1 power. Now you can just go ahead and take the derivative of that. Otherwise, you'd have to do the chain rule and then the quotient rule as part of the chain rule. No, too much. Similarly with 6, right? Number 6, we have a binomial over a monomial, so we can split it up as m to the -1 over m to the -3 plus m to the -2 over m to the -3. And then make sure you subtract, right? So if we were to simplify, it'd be m to the -1 minus -3 plus m to the -2 minus -3. So keep in mind that I think students mess up on the chain rule or the quotient rule or the product rule. So if you have the opportunity to not have to do that, I would encourage you to figure out a way of manipulating or simplifying your expression before taking the derivative. Questions there? Cool. I think that's all I wanted on that one. Good, that's all I wanted there. So here we have the 4 ways of looking at a derivative. So one is just analytical, right? When you have something analytical, all you need to do is take the derivative normally, right? First times the derivative second. Whoops. Derivative of cosine is not cosine. Plus second times the derivative of first. Right, that's easy. And then remember on the test, you do not need to simplify any further. So this would be considered acceptable as long as you show that you know that what the product rule is. All right, how do we approach part 2? We have this one on the right side, the numerical side. What do we do there? So obviously we have a quotient here on top and on bottom, right? Quotient when you divide something. So here's my quotient song, low, D high, minus high, D low, over the square of what's below. So if you were to get this on the test, you get a point for probably writing that out. Then what, you go ahead and plug in the number that they give you to plug in for H. Let's make sure I have this written on the left-hand side just to make sure. K inverse of -1 minus 3K -1 all over 3 times -1 squared. So I'll just put -3 in here. And then probably you'll get another point for doing direct substitution. Yeah, so we need to directly substitute K prime of -1. So K prime of -1 is 4. So that goes in there. And then we have K of -1. K of -1 is -3. So that goes in right there. All right, so then if you can show that you did the substitution, -3 times 4 minus 3 times -3 all over 9, right? That would get you full credit. One more. So we'll do the derivative here really quickly, right? And then somebody tell me what to do because I'm tired of hearing myself talk. So F, oops, first times the derivative second, plus second times the derivative first. We plug in, right? How do we figure out what G prime of 3 is if we want to plug in the value? Anybody? G prime of 3?
We look at the graph.
Yeah.
-2.
How'd you get -2?
That's the slope.
Yep. So when you're looking at a graph, we're looking at the slope of the tangent line around this point, right? And it's nice that it's linear. So you can literally just count boxes. And first, make sure that your boxes are in the same units, right? Because I could totally imagine on the test that they have the boxes, but the boxes equal different things. So the run is 2. The run is 1. The rise is -2. So then we can go ahead and plug in 15 times -2. Right, and then we have G of 3. G of 3 is 0. 0 times 5. And then that would be an acceptable answer. Cool, and then you could get something like this here too, right? You can get a conceptual one where you're gonna have to take the derivative of both sides and just plug in a value. I don't think we need to go over that. Does anybody have any questions? We have 3 ways of looking at it. We have the analytical way where you do what you're taught in class. You have a numerical way or the graphical way. More than likely, you're gonna see numerical or graphical way when you take the tests. Alrighty then. So another thing I want to talk about today is I want to talk about how you interpret these derivatives using words. Because as we all know, the test is going to be in written form most likely. So you want to make sure you're able to express yourself using English to represent calculus ideas. So what are the units of E prime of X? Let E of X be the elevation in feet of the Mississippi River, X miles from its headwaters at Lake Itasca in Park Rapids, Minnesota. Anybody have any idea what the units of E prime of X might be? So you can think about it this way, right? If you have E of X, that E is your Y value, right? That X is obviously your X value. And so another way of expressing E prime of X would be like dy dx. So if you need to talk in units, we can talk about the units here. So what are the units for Y? It'd be feet in elevation per X miles. And then you can copy this whole phrase if you want. So the unit there would be feet per mile though. The next one should be easier. It says, is the sign positive or negative?
Positive.
Why do you think it's positive?
It's elevation. It's going up. The slope's going to go up.
In the Mississippi River from its headwaters. Actually, rivers flow downhill. It'd be amazing if rivers flowed uphill.
Oh.
Yeah. So that's why E prime of X would be negative. Trick question. They probably give you more information. I don't think they expect people to know that rivers flow downhill. Or maybe, is that common knowledge? I don't know. And then part C, calculator permitted, but I don't need you to use the calculator. I just need y'all to know how to set it up. It says find the average change. All right, so we can call this one X1 here, right? We can call this one Y1 if you want. We can call this one X2 and Y2. Right, so if you want to find the average change, you go 0 minus 1475 over 2320 minus 0. And this would be another way to show if the average rate of change is negative, then it's possible that the instantaneous rate of change is also negative. But this would be a way of thinking about it so that you don't miss something like B. All right, number 2, it says an economist is interested in how the price of a graphing calculator affects his sales. Suppose that at a price of P dollars, a quantity of Q calculators are sold. Then the quantity of calculators sold is a function of the calculator's price. That is, Q is equal to F of P. In complete sentences, using correct units, can somebody explain the meaning of F of 150 is equal to 20,000? So what are we plugging in? We're plugging in the value P, right? And that's the price. So we could say
If calculators are sold at a price of $150, then 20,000 will be sold.
exactly. When calculators are sold at a price of 150, then to 20,000 will be sold. Perfect. Right, and that's what you would need to say if you were to get a free response, which you will get a free response. Cool. Now that one's easy. The second one's going to be harder. Does anybody know how to explain part B? When the calculators are at a price of $150, we can say the rate of change of the number of calculators sold. The rate of change of the number of calculators sold is decreasing at a rate of 50 calculators per dollar. And you want to make sure you have the correct units, right? So dy over dx, dy is calculator, dx is dollars. Any questions on that one? Alrighty. Now we have one more set of things I want you to be able to explain. The first one's pretty easy, so I'll just go ahead and explain that one to you. What is T? When the temperature is 50 degrees Fahrenheit. What is M? The number of minutes it takes to boil a cup of water is 19. I'm sure there are more elegant ways of saying that. How do we say the next one though? It's backwards, isn't it? So I guess you can just reverse the statement, right? Inverse functions are basically switching the x and the y around. So when, yeah, I guess you could say if it takes 19 minutes to boil, then the initial temperature was 50 degrees Fahrenheit. I missed the word initial in the first one, don't forget that. And the initial temperature is 50 degrees. Part C. If the initial temperature is 50 degrees Fahrenheit, then the rate of change in minutes per degree Fahrenheit is increasing at 3, something like that. And then part D, we have the inverse function. So what do we input in the inverse function? We put the number of minutes, right? If the number of minutes it takes to boil is 18 minutes, then the rate of change, and so now since we're doing the inverse function, we have to switch the dx and the dy, right? So it's going to be dx over dy. The rate of change is increasing at 0.2, what is the dx here? Degrees per minute. Any questions there? Alrighty, and then the last thing I wanted to get to today, and then I'll give you some questions to work on, is all these theorems that you have. Right, somebody yesterday was asking about Rolle's theorem and mean value theorem. So we have mean value theorem here. So make sure that you take this and put it in somewhere where you can easily access this, because this is a very likely question you might get asked too. So what are the two hypotheses, or what are the two conditional statements you need to satisfy? That f is continuous on the closed interval, a to b, and that f is differentiable on the open interval, a to b. Earlier, Joey was asking the question, like, why does it need to be the open interval? Just because at the end, let's say your function ends right there, you can't take the derivative at an endpoint, right? Because maybe there's no piece of the function on the other side connecting to it. So I think that's why this one has the open intervals for the differentiable part. And then the way I say mean value theorem is, if we satisfy these two statements, then we can say AROC is equal to IROC. The average rate of change is equal to the instantaneous rate of change. So this one's AROC right there, and then this one's IROC right there. In fact, I'm just gonna switch them just so it matches along with the notes that are given. There is a value of C such that the derivative is equal to the average rate of change. Any questions on that one? So then we have mean value theorem, and then we can also do something called Rolle's theorem. Rolle's theorem is literally the same exact thing as mean value theorem, except the only difference is f of a is equal to f of b, or we can rewrite it as f of b minus f of a is equal to 0. So Rolle's theorem is just the specific instance where you try to calculate the difference between the 2 points and you see that there's no difference. Right, so literally, if you were to connect the dots, it'd be a horizontal line between them. So when you're justifying these things on the test, you don't necessarily need to say I'm using mean value theorem, or you don't need to say I'm using Rolle's theorem. You actually need to show that you're satisfying the conditions though. So you need to say that f is continuous and differentiable on the interval a to b. Does anybody have any questions about mean value theorem or Rolle's theorem? So then here I put a couple of really recent AP questions. This one came from the test last year. This is question number 2. And the first thing they ask you is justify why there must be at least one time t for which t is in this interval 0.3 to 2.8, at which v prime of t, aka the acceleration of the particle, equals 0 meters per hour per hour. Right, so when you see justify, you should think that you're probably going to use IVT or MVT / Rolle's theorem. And then which one do we use? Well, we use IVT when they're talking about the value of the function given. And then we use MVT when they're talking about the derivative of the function given. All right, so here we're going to use mean value theorem. So let's check for the conditions, right? What do we need? We need the function to be continuous and differentiable on the interval. Well, let's read the opening part. It says the velocity of the particle p is moving along the x-axis given by the differentiable function v sub p. And at this point, I've like harped on it so many times. You should know that if differentiable, then continuous, right? So you could start with a sentence saying v sub p is differentiable You can use therefore or thus if you want. Thus, it is also continuous. And then you probably want to put the intervals, right? So V is differentiable. Does it say for all real numbers? It doesn't, but I think you can just see this. This is differentiable along its domain. Thus, it is also continuous along for all t. And I'm going to bring back this that trident type thingy, right? T 0.3 to 2.8. And then you could say therefore. And then you can literally just copy the question. There is at least one value. At least one value of t for which v prime of t is equal to 0. And then to fully get the point, you also need to show the slope, right? So let's take the slope here. We have, this is our x1, this is our x2, this is our y1, this is our y2. So let's show the slope then. It's 55 minus 55 over 2.8 minus 0.3 is equal to 0. So I think as long as you show that you're taking the average rate of change here, as long as you show a statement that shows that you know that the function must be continuous and differentiable, and as long as you have this concluding statement there, you should get all the points for this question. Any questions about how to use mean value theorem? Okay. So then we have this one from 2007, the AB exam. Part A is easy, right? We literally just did part A in a different question, so we don't need to do part A. But what about part B? Show that G prime of 2 is equal to G prime of 5, and use this result to explain why there must be a value of K for K between 2 and 5, such that G double prime of K is equal to 0. Anybody have any suggestions on what I should do first? So let's do this one first, right? Let's take the derivative of both sides. So g of x is equal to f of x. Let's take the derivative of both sides. G prime of x is equal to, chain rule, right? Derivative of the outside, don't touch the inside, times the derivative of the inside. Bloop. And then we need to figure out 2 and 5, right? So let's see, what is g prime of 2? G prime of 2 is equal to f prime of f of 2 times f prime of 2. F of 2 is equal to 5, f prime of 5, times, what is f prime of 2? Oh, I think I'm missing part of this question that we can't do it. Well, let's write it this way. Maybe I'm not missing part of the question, because I think what's going to happen is we might get the same number. And then we have, let's do g prime of 5. G prime of 5 is equal to f prime of f of 5 times f prime of 5. Haha, so they tried to trick me. So then we get f prime of 5 is equal to 2, or sorry, f of 5 is equal to 2. So then we get f prime of 2 times f prime of 5. Wow, what a sneaky question. So look at that. We have g prime of 2 is equal to that. We have g prime of 5 is equal to that. So then I just showed that g prime of 2 is equal to g prime of 5. So that's the first part. And now we can go through that whole step again, right? So what do we need to check? We need to check if it's continuous and differentiable along the domain. So let's see, it says it's twice differentiable, right? So we can say, I'm just gonna use shorthand. So continuous, differentiable. These 3 dots means therefore, G double prime of K equals G of 5 minus G of 2 all over 5 minus 2 is equal to 0. This is my shorthand notation. Please use complete sentences when you're writing this out on your test. Who has thoughts? Who has questions?
When we're writing the answers, do we have to cite which theorem we're using?
You do not have to cite it. It's helpful if you cite it. So you can say, because the function is continuous, because the function is differentiable, mean value theorem states that. But you don't have to actually say mean value theorem. Other thoughts? You could also say Rolle's theorem here if you want to. You can roll with the punches. Alrighty, so there is some time, so I get to do some true false questions with you. I have 4 questions here. So you need to tell me if it's true or false, and then if it's false, come up with a counterexample. Or tell me why it's false. Right, so A says the slope of a tangent line to a differentiable function f at the point 2 comma f of 2 is equal to that thing. Is that true or false? Part B, if a function is continuous at a point, then the function is differentiable at that point. Is that true or false? C, if a function slopes from both the left and the right at a point are the same, then that function is differentiable at that point. And then D, if a function is differentiable at a point, then that function is continuous at that point. Put on your thinking caps. I'll wait a couple more seconds. See if there's any stragglers who want to vote. Aha. So here are the results that we have. So 80% thought that number 1 is true. Number 1 is false. we need to figure out that the limit as h approaches 0, right? We remember that we said the slope of the tangent line is equal to the derivative. And then the derivative is equal to the instantaneous rate of change. So the expression they gave you in part A is just the average rate of change. So don't forget to write limit in case you get a limit notation question for derivative. Part B, 80% of you said it's false. Why is it false? Can somebody give me a counterexample?
A function can be continuous, but it can have like a cusp or something where the slope would be different coming from the left and the right. So it would be differentiable.
Cusp, kink, something like that, right? So keep that in mind. So this one's a very common question. Part C, 80% of you said it's true. C is actually false. So for something to be differentiable, not only do the slopes from both points have to be the same thing, but the point itself also has to be the same thing. So let me give you an example, right? What if we had a line here, right? And it has a slope. And what if we had another line here, right? And it has the same slope. They both, the limits of the slope are the same, but then at that point itself, it's not equal. So remember that it has to be continuous in order for it to be differentiable. So C is false. And then of course D, right? I've said it a million times, D is true. Any questions on this? So I got through everything that I wanted to get through really quickly. So I don't know if people want to redirect this lesson a little bit and ask questions and I can work through some more problems. If not, I have some extra problems prepared. I'll let you all decide. Any questions from sections 1 through 3, units 1 through 3, derivatives and limits, continuity, differentiability?
For limits at infinity, is it just looking at a growth chart and just kind of logic?
You can, right? Yeah, if you want to evaluate limits at infinity, you can just use Desmos or something like that and look at it. However, right, remember I gave you this type of question yesterday where you know that you might not have two horizontal asymptotes that are the same value. You could have two different horizontal asymptotes, right? So for example, for number 6 on this one, we could say the limit here as x approaches infinity of this one is going to equal the square root of 4x squared over 3x, right? And then remember that the square root of 4x squared can also be written as absolute value of 2x over 3x. So the limit at positive infinity is 2/3. Likewise, the limit here as x approaches negative infinity is equal to negative 2/3. And then you could use Desmos to see that this is indeed true. Does anybody else have other things that they want me to hit upon? Alrighty, look at question number 8 then. So given the selected values of the continuous function h of x, what is the fewest number of times h of x is equal to 43 on the interval? I'll let y'all type in the chat box if you want to come up with an answer. I guess see one answer. And thank goodness it doesn't say to justify here. Right here, if we look at this, right, this interval, it goes from 100 to 5 and it's continuous, right? So then it has to pass through 43. Goes from 40 to 40, it could, but we don't know, right? It goes from 40 to 110, true. It goes from 110 to 30, true. 30 to 10, we don't know. And then 10 to 50, it passes back through 40. So there's 1, 2, 3, 4, 4. Okay, that one's not bad. All right, look at number 9. Let's have you see if you can evaluate this interval and then give me the answer. We're given that the limit of v as x approaches 7 is equal to 6. The limit of v as x approaches -7 is 3. And then the limit of c, which is a different function, keep this in mind here, different functions, is equal to 5. Evaluate this limit. So one thing is, since it says it's continuous, right, we don't need to do the plus or the minus sign, right? So we can just kind of ignore it. So we can just evaluate the limit at 7, right? And when we evaluate the limit at 7, it's v of -7 minus 5c of x. And since this 7, excuse me, not x. And since the function is continuous, we can literally just yoink these values down, right? So it's just 3 minus 5 times 5 is -22. So those who responded to me are correct. One more from section 1, and then I'll give you some more complicated questions. Find the limit of this thingy, x squared sine of 1 over x. So whenever you get sine or cosine, remember we can start stacking that function. Right, sine of x, or sine of 1 over x, excuse me, is always going to be between 1 and -1. right? Whatever that function is. And then what? We can kind of stack the x squareds on all three sides then, right? So we can say x squared, oops, that should be negative. Negative x squared is less than or equal to x squared sine of 1 over x is less than or equal to x squared. Right, so I just times everything in this interval by x squared. And then what? Well, I can evaluate the limit of the other two, right? So limit as x approaches 0 of x squared is equal to 0, right? Is also equal to limit as x approaches 0 of negative x squared, right? So if the two endpoints of the inequality have a limit of 0, then guess what? The limit of this thing is also equal 0. Who remembers what that's called?
Squeeze theorem?
Squeezy poo, squeeze theorem. Yeah, so in case you have to use that, you could evoke squeeze theorem. Alrighty, so that's a review of the harder ones on the homework assignment. And then I have this thing that I also want to have y'all do. These are a little bit more crazy. So let's have you all do the numerical one. See if y'all can give me an answer for the numerical one. Cool. It's negative 12. Y'all are right, right? So it's f prime of f of x times f prime of x. And then you just plug in 1 for all that values and y'all got negative 12. Awesome. And then I'll just write out the solution for you later since y'all are really good at that. And then let's do this conceptual one. Okay, this one's a little bit of a step up. See if y'all can do that one. It says g is a linear function with g of 3 is equal to g prime of 3 is equal to 4. Find the derivative of k at 3. I'll even be nice and write out the quotient rule for you. Low d high minus high d low. All over the square of what's below. I'll even plug in the 3 for you. We get g of 5, g prime of 3, minus g of 3, g prime of 5, all over g of 5 squared. This is another one where they make you think like you're missing something. We can even go ahead and start placing the things that we know in. We have G of 5. Oh, that's a weird looking 5. We know that G prime of 3 is equal to 4. We know that G of 3 is equal to 4. We're stuck with these G's of 5 and G primes of 5. What the heck? Does anybody have any idea where to go with that? Torturing y'all. It says G is a linear function, yeah? So guess what? If we have a linear function, this slope is always going to be 4, right? Because the derivative is just the slope of the line, the slope of the tangent line. And the slope of the tangent line is always going to be 4 if it's a linear function. So then I can go ahead and replace my G prime of 5 with the number 4. So this one's a 4. Then how do we figure out this G of 5 then? Well, we can recreate our tangent line, right? We know that if G of 3 is equal to 4, then my coordinate on my graph is 3, 4. And then we can come up with my equation. And I'm going to do my equation in Taylor form, since some of you are thinking about Taylor series right now. So in my Taylor form, my equation is y is going to equal the point. I'll be a little bit more specific to that. Y is equal to G of 3 plus G prime of 3 x minus 3. That's the equation of my line in Taylor form. So then y is equal to 4 plus 4x minus 3. Now I can plug 5 into this equation. This is my tangent line equation. All right, so that's my tangent line equation. I plug in 5. What is G of 5? It's 4 plus 4 times 5 minus 3 is 2. So then G of 5 is equal to 12. So then we get here is 12 times 4 minus 4 times 4 over 12 squared is my answer. And then I got a question. How did I get that G prime of 5 is equal to 4? Well, let's think about it. G is a linear function, right? So let me zoom out a bit. If I were to draw a linear function, this is my function right here, linear function, right? And then the derivative is the slope at any point along that line. Well, it's a linear function, so the slope is always going to be 4 because it's a line. So just based off of that word linear, we know that every G prime of 10, G prime of 2, G prime of infinity is always just going to equal 4. Does anybody have any questions on that one? This could totally be fair game because this is not something that you could Google and then like plug into a calculator online. Cool. So I try to cram all the derivative stuff. So I would encourage you, if you need to make a list of derivatives or find a list of derivative tables. And then you can just have that list of derivatives in case you need it. I don't think you'll need it. We'll see. But know how to take all these derivatives conceptually, right? Using f of g, f of x, g of x, that sort of stuff. And then what we're going to do tomorrow then is we're going to take all this stuff and we're going to do applications of derivatives. So we're going to do related rates. We're going to do optimization. We're going to try to minimize and maximize values. Okay. I'm going to post all my notes in Dropbox. I'm going to post some extra homework assignments. So the ones from yesterday should be up. I'm going to post these things called circuits. So basically all the answers are on the page and there's like 10 boxes. And like, if you do one box, it should give you the answer to the next box. So then all the answers are on the page. So if you can solve the page, then you know you've gotten the concept right. Any thoughts? questions, concerns? Alrighty, everybody have a good day. Let me know if you have any questions via email.
Thank you.
Bye.
Uh,
Peace.